SwayamPrabha. Digital India. Educated India.
In the last module, we have discussed the first step of kinematic analysis under the title displacement analysis. Today, we shall start the second step of kinematic analysis, which we call velocity analysis. By velocity analysis, we mean that for a given mechanism at a particular configuration, if the input velocity characteristic is specified, we should be able to determine the velocity characteristics of all other links of the same mechanism. So, let me repeat. By velocity analysis, we determine the velocity characteristics, which may be linear velocity of a point or angular velocity of a link, of all the links of a mechanism at a given configuration when the input velocity is specified. So, by velocity analysis, basically we mean the velocity analysis of interconnected rigid bodies in plane motion, because we are discussing only planar linkages. But before getting into the details of this velocity analysis of interconnected rigid bodies, let me recapitulate some basic points of the kinematics of one rigid body which is under plane motion. So, plane motion of a rigid body, some basic points let me recapitulate first. We should remember that in plane motion, the angular motion of a rigid body is the same as that of a line on that rigid body in the plane of motion. This we will explain a little later. Second point is that the angular velocity and angular acceleration vectors of that rigid body are always perpendicular to the plane of motion. Because the rigid body is in plane motion, all angular quantities will be represented by vectors which are perpendicular to this plane of motion. We should also remember that a general plane motion consists of translation of the rigid body plus rotation of the rigid body. In a mechanism, a particular link may be undergoing pure rotary motion, another link may be undergoing pure translatory motion, but there may be some links which undergo both translation and rotation simultaneously. What we mean by translation is that if a body is under pure translation, then all points on that body have identical motion. The difference between the motion of 2 points on a rigid body is entirely due to its rotation. So, translation means identical motion of all points, and if there is rotation, then there will be difference in the motion between various points of the same rigid body. Let me now explain these points with reference to this figure. Here we have a rigid body in plane motion, and the plane of motion is the plane of the screen. Let at a time instant t, the rigid body is in this configuration 1. After a small interval of time, say delta t, that is at time t plus delta t, the rigid body comes to this configuration which is given by 2. So, during time delta t, the rigid body moves from configuration 1 to configuration 2. And we consider 2 points on the rigid body, namely B and C. We say B1, C1 are the locations of B and C at configuration 1, and B2 and C2 are the locations of the same points B and C in configuration 2. Now, this is a general plane motion of this rigid body. As I said, the plane of motion is the plane of the screen, let us say x and y. X, y is the plane of motion. So, all angular quantities like angular velocity or angular acceleration of this rigid body will be perpendicular to the plane of motion, that is perpendicular to the screen, which we will denote by the z axis with a unit vector k. As I said earlier, for this plane motion, the angular motion of the rigid body will be same as the angular motion of a line on this rigid body, for example, the line B1 C1. So, what we see that the line B1 C1 has come to the position B2 C2. So, the line B1 C1 has moved and also rotated and occupied the position B2 C2. So, if I draw B2 C1 prime, which is parallel to B1 C1, and then we can see the rotation of this line B1 C1 during this time delta t is given by delta theta. So, let us consider this general plane motion of this rigid body during the time interval delta t when it moves from configuration 1 to configuration 2. This can be decomposed under two headings, namely a translation which takes from configuration 1 to configuration 1 prime, when all the points move by the identical amount and in identical direction. That means B1 goes to B2, C1 goes to C1 prime by the same amount. All points of the rigid body move identically and the rigid body goes from 1 to 1 prime. That is what we call translation. Then from 1 prime to 2, the point B2 does not move, it undergoes rotation by an amount delta theta. So, the angular velocity vector of this rigid body can be defined as omega is limit delta t tending to 0 delta theta by delta t, and the direction of this vector is along z, which I write as the unit vector k. So, angular velocity vector comes out as theta dot, that is the derivative of theta with respect to time in the direction k. Similarly, angular acceleration of this can be written as alpha, which is second derivative of theta with respect to time, that is theta double dot, and in the direction k. So, this is what we mean by the general plane motion of the rigid body in the xy plane with angular velocity vector omega and the angular acceleration vector alpha. Now, as we see, during the translation there is no difference between the motion of various points of the rigid body like B and C. They underwent identical motion. The difference in motion between C and B is entirely due to rotation, that is due to this angular velocity vector omega. Positive k means counterclockwise direction. Now, the difference of velocity between the points C and B, let me write it as difference of velocity of the point C minus velocity of the point B. This is the difference of velocity. We use a symbol V C B. As we have noticed, this is entirely due to the rotation of the rigid body. That means the point C with respect to B moves in a circle and the angular velocity of the line BC is omega. So, from our basic knowledge of dynamics or kinematics of rigid body, we know that for this circular motion, this difference of velocity is given by omega cross the vector BC. So, this is one very basic result which we will be using very frequently in our subsequent velocity analysis, that if we consider two different points B and C on the same rigid body whose angular velocity is omega, then the difference of the velocities Vc minus Vb is given by omega cross Bc. Now we consider the difference of acceleration between these 2 points, namely C and B. As we have already noticed, with respect to B, the C is going in a circle and the angular velocity, because the distance BC never changes, so C goes on a circle with B as center, and the angular velocity of the line BC is omega, and the angular acceleration of the line BC is alpha, which are nothing but the angular velocity and angular acceleration of the rigid body. So now we can write the difference of acceleration between these 2 points, namely AC minus AB, that as usual before I use the symbol ACB. This is the difference between the acceleration of the 2 points, namely C and B, on the same rigid body. That is given by, there is a centripetal acceleration due to the circular motion, which is given by omega cross BC, and there is a tangential component which along the vector T1, that is given by alpha cross BC. Because omega vector is along the k direction and the BC vector is in the xy plane, it can be easily shown that this will always turn out to be, the first term will be omega square CB, that is towards B from C, that is the vector CB, and the magnitude will be omega square into BC, and the tangential component will be alpha cross BC. That means it will be perpendicular to the vector BC in the sense of alpha. If alpha is counterclockwise, then it will be in this direction. If alpha is clockwise, then it will be in the opposite direction. So we get the relationship between the difference of 2 points of the velocity like B and C given by omega cross BC. At this stage, we should note that if we know the velocity of any point, say namely Vb, which is a 2-dimensional vector, that is 2 components of Vb, and the vector omega, that is the angular velocity of the rigid body, then I can determine velocity of any other point, namely C, using this relation, that is velocity of any other point C, Vc, can be obtained from Vb plus omega cross Bc. We should note that there can be only 3 independent unknowns, namely 2 components of Vb and omega. Then velocity of all other points on that same rigid body is completely determined by this equation. Similarly, if we are given acceleration of a particular point AB, which has 2 components, that is 2 unknowns, and the angular velocity vector omega and the angular acceleration vector alpha, then acceleration of any point C can be determined using this equation, that AC will be AB plus these 2 components. So there can be 4 unknowns, namely 2 components of AB and omega and alpha, and then all acceleration of all other points on that same rigid body is completely known. These 2 information, as we shall see later, will be very useful for velocity analysis of mechanisms. Now that it is clear how to correlate the velocity and acceleration of 2 points on the same rigid body, let us develop another very important concept for velocity analysis, that is called instantaneous center of velocity, or in short IC. For a rigid body in plane motion, we will be able to show that always there exists a point on the rigid body, of course in the plane of motion, whose instantaneous velocity is 0. And this point is called the instantaneous center of velocity, or IC. It must be mentioned that this IC may lie outside the physical boundary of the rigid body, but it lies in the plane of motion of that rigid body. If a rigid body is under pure translation, then obviously no points has 0 velocity. In that case, we say that the IC lies at infinity in the direction perpendicular to the direction of translation. Just like a prismatic pair we considered as a revolute pair in a direction perpendicular to the direction of sliding. Let me now show that there does exist such a point, that which we call the instantaneous center of velocity. To prove the existence of instantaneous center of velocity for a rigid body under plane motion, let us consider this figure. We consider 2 points, namely A and B, whose velocities are given by Vb and Va. We have already seen that if Va is given and omega is given, then Vb is completely determined. That means both Vb and Va having 4 components cannot be independent. Now, let me draw perpendicular to these velocity vectors. At B, I draw the line Bi, which is at 90 degree to Vb. And at A, I draw a line Ai, which is at 90 degree to the velocity vector Va. These two perpendicular lines drawn at A and B meet at I. We will show that the velocity of this point I of the rigid body at this configuration must be 0, and that is what is called the instantaneous center of velocity for this configuration. To show that Vi is 0, let us consider the component of the velocity Va in the direction of AB. That will be Va cos theta. Va cos theta is the velocity of A in the direction AB. The component of Vb in the direction of AB is Vb cos phi, where phi is the angle between the direction Vb and the direction AB. Now, the distance AB never changes. That means these two velocity components must be same. That is, the component of Va along AB must be same as the component of Vb along AB, because the distance AB never changes. So, I can put Va cos theta is same as Vb cos phi. Now, if I consider the triangle IAB, let us consider the triangle IAB. Because IA is perpendicular to Va and IB is perpendicular to Vb, we can easily see that this angle is pi by 2 minus phi, and this angle, that is between IA and AB, is pi by 2 minus theta. So, considering this triangle IAB, if we use the sine law, I can write IA divided by sine of IBA, that is sine of pi by 2 minus phi, that is cos phi, is same as IB divided by sine of the angle IAB, that is sine of pi by 2 minus theta, which is cos theta. So, we get from this equation Va divided by cos phi is same as Vb divided by cos theta. And from the geometry we get Ia by cos phi is same as Ib by cos theta. So, I can easily write Va by Ia is same as Vb by Ib, and this ratio I call omega, that is the angular velocity of the rigid body. So, Va is Ia into omega and Vb is Ib into omega, and the velocity vectors Vb and Va are by construction perpendicular to the direction of Ia and Ib, which means I is the center of rotation. At this instant the body is rotating about the point I with angular velocity omega. In fact, you can also prove that velocity of I is 0 by considering the velocity of the point I in two different directions, namely Ia and Ib. To find the velocity of the point I along Ia, I come from the point A. Velocity of A is along Va, so the component along Ia is 0, and I and A are 2 points on the same rigid body. So, velocity of I along Ia is also 0, because the relative velocity of A and I along Ai is 0. Velocity of A along Ai is 0. Velocity of I with respect to A along Ai is also 0. So, velocity of I along this direction Ai is 0. Coming from the point B, I see that the velocity of the point B is perpendicular to Ib. So, component of Vb along Bi is 0. So, velocity of I along Bi is same as the velocity of B along Bi. So, velocity of I along Bi is also 0. Thus, the velocity of the point I is 0 along two directions, along Ai, and it is also 0 along Bi. So, if Vi is a two dimensional vector and if it is 0 in two different directions, then velocity of I must be 0. So, we get velocity of the point I, which I write Vi, is 0 at this configuration, and this is what is called the instantaneous center of velocity. Now that we have explained the concept of instantaneous center of velocity, let us extend this concept between two moving bodies. Previously we said one rigid body which is moving and there exists an instantaneous center of velocity. Now let us consider two moving bodies, say numbered 2 and 3. Then we can define a relative instantaneous center, say I23, as a point on body 3 having 0 relative velocity, that is same absolute velocity with respect to a coincident point on body 2. Let me repeat, we are talking of two moving rigid bodies, say number 2 and 3. We define a relative instantaneous center between these two bodies 2 and 3. I call it I23. What is I23? Now, this is a point on body 3 having 0 relative velocity with respect to a coincident point on body 2. So, from this definition it is very clear that I23 is same as I32. In light of this relative instantaneous center, we can redefine the absolute instantaneous center of velocity, which we discussed earlier, as the relative IC with respect to fixed link 1. As you know, in mechanism there will be a number of rigid bodies, interconnected rigid bodies in plane motion, and there is a fixed link which we always numbered as 1. So, out of this n link, any n link mechanism, we will have a number of relative instantaneous centers, and the relative instantaneous centers with respect to the fixed link 1 are nothing but the absolute instantaneous center of velocity, that is at that instant that particular body is rotating about that instantaneous center. So, if we have an n-link mechanism, then according to this kind of definition of relative ICs, we will have NC2, that is 2 links taken at a time. How many different combinations we can make, that is NC2 or n into n minus 1 by 2 relative ICs. So, for an n-link mechanism, we will have n into n minus 1 divided by 2 so many numbers of relative instantaneous centers. At this stage, let us discuss how, by looking at the interconnections between various rigid bodies in a mechanism, we can determine the relative instantaneous centers. As you know, in a planar mechanism, rigid bodies will be connected either by revolute pair or by prismatic pair or by some kind of higher pair. So, if two bodies are connected by a revolute pair, then the relative instantaneous centers between those two bodies is obviously at the center of the R pair, because as the mechanism moves, the center of the R pair between these two bodies always move together. So, there is no relative velocity between those two coincident points of the two rigid bodies connected by the R pair. The center of the R pair will be the relative IC. If the two bodies are connected by a prismatic pair, then the relative instantaneous center is at infinity in a direction perpendicular to the axis of the P pair, because if the two bodies are connected by a prismatic pair, then as we know, the relative motion is a pure translation, and in case of translation, the instantaneous center lies at infinity in a direction perpendicular to the direction of sliding. We can recall that a P pair is nothing but an R pair at infinity in a direction perpendicular to the direction of relative sliding. So, these two sentences imply that a P pair, for a P pair, the relative IC is at infinity in a direction perpendicular to the axis of the P pair. Suppose we have a higher pair with a kinematic constant, that one body rolls over the other without slipping. That means it is not a normal higher pair, it is a higher pair with a kinematic constant that there is no slip at the point of contact. So, from no slip condition, I know that velocity of the 2 points of contact belonging to two different bodies must be same. That is the condition for no slip. Consequently, the point of contact itself will be the relative IC between those two bodies which are connected by a higher pair without slip. But for a general higher pair where slipping is allowed, that means one body simultaneously rolls and slides over the other, when it constitutes a general higher pair, then the relative IC lies somewhere on the common normal at the point of contact. We cannot determine it exactly where on this line common normal it will lie, that requires some other information, but we know that it must lie on the common normal at the point of contact. At this stage, let me say that there is a very important theorem called Aronhold-Kennedy theorem of 3 centers, which will be very useful to determine all the relative ICs of a mechanism along with the information that we have just now discussed. That is, at the R pair, the relative IC is at the center of the R pair. At a P pair, the relative IC is at infinity in a direction perpendicular to the direction of relative sliding. If it is a higher pair without any slip, then it is at the point of contact, and if it is a general higher pair with slip, then it is somewhere along the common normal at the point of contact. With this information plus the application of Aronhold-Kennedy theorem, we should be able to determine all the relative ICs of planar mechanisms having up to 6 links, which is sufficient for our purpose. So, next let me state and prove the Aronhold-Kennedy theorem. So, Aronhold-Kennedy theorem of 3 centers is the following. If 3 rigid bodies are in relative motion, we are talking now 3 rigid bodies which are in relative motion, but they may not be interconnected. But with 3 bodies we have 3 relative ICs, because 3C2, that is 3 into 3 minus 1 divided by 2 gives you 3. So, 3 rigid bodies in relative motion, there are 3 relative ICs. The Arnold-Kennedy theorem says that these 3 relative ICs must lie on a line, that is, the 3 relative ICs are collinear. We shall prove the Arnold-Kennedy theorem by contradiction. That means, we will assume them to be non-collinear and show that that is impossible, which means they have to be collinear. To prove Arnold-Kennedy theorem, let us consider 3 rigid bodies, namely 1, 2 and 3, which are in relative planar motion. Because we are considering relative motion, we do not lose any generality if I assume one of the bodies to be fixed. So, let me assume that body 1 is fixed, as indicated by these hatched lines. So, to consider the relative planar motion between 3 rigid bodies, namely 1, 2 and 3, I consider the body 1 to be fixed. And let us say that I12 is the relative instantaneous center for body number 1 and 2. Similarly, I13 is the relative instantaneous center between body number 1 and 3. That means, at this instant body 2 is under pure rotation about the point I12 with respect to body 1. Similarly, body 3 is under pure rotation about the point I13 with respect to body 1. Now, let us say that Arnold-Kennedy theorem is wrong. That means, the instantaneous center I23 need not lie on the line joining I12 and I13, and let us assume it is at this location I23 prime. Now, if I23 prime is the relative instantaneous centers between body number 2 and 3, then it must have the same velocity whether I consider it to be a point on body 2 or I consider it to be a point on body 3. That is the definition of relative IC I23. If I consider it to be a point on body 2, it must have the same velocity if I consider it to be a point on body 3. That is the definition of I23. But suppose it lies here, then this vector velocity I23, if I consider it to be a point on body 2, must be in this direction, that is perpendicular to the line joining I12 and I23. This is the line I12, I23, then velocity of this point as a point on body 2, which is rotating about this point, must be in this direction, perpendicular to this line. But if I consider this point to be a point on body 3, which is rotating at this instant about I13, then the velocity must be perpendicular to this line joining I13 and I23, that is in this direction. And these two directions are different, so this equation can never hold good. This equation can never hold good because these two vectors Vi23 as a point on body 3 and Vi23 as a point on body 2 are in different directions. So, we immediately get a contradiction. These two vectors can have same direction only if I23 lies somewhere on this line, say here or there or there or there. Then only the rotation about I12, if I consider it to be a point on body 2, which will be perpendicular to this line, and if I consider it to be a point on body 3, which is rotating about I13, also is perpendicular to this line. So, these two velocity vectors can have the same direction, which is necessary condition for it to be the relative instantaneous center I23. So, we have proved Arnold-Kennedy theorem of 3 centers by contradiction, and now I will demonstrate this by use of a model. Let me now try to explain both the concept of relative IC and the application of Aronhold-Kennedy theorem with the help of this model. In this model, as we see, we are talking of three rigid bodies in relative motion, namely one which is the fixed link, two this is this red body, and three that is this blue body. So now 1 and 2 is connected by a revolute pair here, so immediately I locate the relative instantaneous center 1, 2 at this point. Similarly, body 3 which is connected by a revolute pair with 1 at this point, I consider this as 1, 3, the relative instantaneous center 1, 3. Now 3 and 2 has a higher pair at this point of contact. So we are talking of three rigid bodies, namely 1, 2 and 3. 1 and 2 has a revolute pair here, 1 and 3 has a revolute pair there, which means I have located two relative instantaneous centers, namely 1, 2 and 1, 3. Now the relative instantaneous center 2, 3 I know must lie along the common normal at this point of contact. This is a general higher pair. We have already discussed that in case of a general higher pair, the relative instantaneous centers, in this case between body 2 and body 3, that is I2, 3, must lie on this common normal. And we also know from Aronhold-Kennedy theorem that 1, 2, 1, 3 and 2, 3 must be collinear. That is how we determine the location of 2, 3 at the intersection of this common normal and this line joining 1, 2 and 1, 3. 1, 2, 1, 3 and 2, 3 must be collinear and 2, 3 must lie on this common normal. That determines this location 2, 3. So this is the relative instantaneous center 2, 3 between two moving bodies 2 and 3. By definition, at this instant, if I consider this point to be a point on body 2, that is this red link, or a point on body 3, that is this blue link, they have the same velocity. So as we will notice that around this configuration, these 2 points on body 2 and body 3 at the location of I2, 3 move with same velocity. However, these 2 points now as we see have moved differently. This is a point 2, 3 on body 2 and this is the point 2, 3 on body 3. At this location, at this configuration, their velocity is the same. So around this configuration, they move almost with same velocity. At this instant, with exactly same velocity, around that region, almost with same velocity, so there is not much of separation. However, when they have moved a lot, as we see, that point 2, 3 which was here as a point of body 3 has come here and as a point on body 2 has come here. I hope this clears both the concept of relative instantaneous center and the application of Aronhold-Kennedy theorem, which we shall continue subsequently. Let me now summarize what we have covered in this lecture. We started with the general plane motion of a single rigid body and have shown that if we know the velocity of any point on that rigid body and the angular velocity of the rigid body, then we can determine the velocity of all other points on that rigid body. Then we have shown that if we know the acceleration of a point on that rigid body and the angular velocity and angular acceleration of the rigid body, then acceleration of all other points on that rigid body can be determined. Next, we showed the existence of the so-called instantaneous center of velocity. That means, for a rigid body in plane motion, there exists a point about which at that instant the body can be considered to be under pure rotation. Then we extended the concept of instantaneous center to relative motion of between two moving bodies. Then we defined relative instantaneous center exactly the same way. Finally, we have stated and proved the Aronhold-Kennedy theorem of three centers, and finally we have shown the concept of relative instantaneous center and the application of Aronhold-Kennedy theorem for determining all the relative ICs of a particular mechanism. In our next lecture, we will continue with the application of these instantaneous centers, their determination and their use for continuing the velocity analysis of planar mechanisms.